Laminar means smooth, and so laminar blood flow is blood that's flowing smoothly through the vessels. Turbulent flow, on the other hand, is when the blood's not flowing smoothly, and we can figure out if blood's likely to be laminar or turbulent by finding its Reynolds number, or RE, which is named after Osborne Reynolds, a Victorian scientist who not only studied fluid dynamics, but is a man who knows how to rock a beard and bow tie. Now, if everything's moving like it should and blood flow is laminar, then the linear velocity of the blood, which is how fast it's moving in a straight line, is greatest in the center of the blood vessel, and lowest near the walls of the vessel, dropping to 0 at the wall. Sometimes, though, blood flow is disrupted, like if it has to pass by a crusty old atherosclerotic plaque buildup along the wall, which ends up reducing the diameter of the blood vessel at that point and causes turbulence. Now, there are a number of factors that help predict turbulence, and they include the density of the blood, usually written by the Greek letter rho, as well as the viscosity of the blood, denoted by the Greek letter eta. You can think of a fluid's viscosity as kind of like its thickness. Like, for example, the viscosity of honey is a lot greater than that of water. After that, there's the velocity of blood flow, or just V, and then finally there's the diameter of the blood vessel, or D. These can all be used to come up with a single value, the Reynolds number, and the equation goes like this. Reynolds number equals density times diameter times velocity, all over viscosity. Generally speaking, if the Reynolds number is low, below about 2,000, then blood flow will be laminar. Think L for low and L for laminar. But if the Reynolds number is above 3,000, it'll likely be turbulent. A Reynolds number between 2,000 and 3,000 is somewhere in between. As a real-life example of turbulent blood flow, a person with anemia has a low red blood cell count, and in general has a lower hematocrit, which is the ratio of the volume of red blood cells to the total blood volume. This essentially means that the blood's less thick, or viscous. Based on the equation, if viscosity decreases, that means Reynolds number increases. Also, these individuals often have an increased cardiac output, which means increased blood velocity and therefore increased Reynolds number. Now, another example would be a person with a thrombus, or a blood clot, which just like atherosclerotic plaque would narrow or decrease the diameter of a blood vessel. Now, at first glance, this seems a little weird, huh? Since it looks like a decrease in diameter should probably decrease Reynolds number. But it turns out that the blood velocity also depends on the diameter of the vessel, by the equation velocity equals flow rate Q over area, where the area is the area of a circle, which is pi times d over 2 squared. And this comes out to be 4Q over pi d squared. Taking that guy and plugging it in for velocity, we now see that as the diameter decreases, Reynolds number increases. Now, a related concept is shear. And remember that blood velocity depends on whether it's in the middle, which is where it's the fastest, or it's near the walls, where it's the slowest. In fact, at the molecular level, just outside the walls, water molecules are just sort of sitting still and not moving. And if we freeze this and then plot those velocities, we'll notice that the difference between adjacent velocities is parabolic, meaning that as you move away from the walls, velocity at first jumps up pretty quick. But as you get near the middle, the change in velocity is actually pretty low. This difference in relative velocities of adjacent layers is called shear. So if we wanted to also plot the shear, near the wall the velocity is changing the most, right? So shear is actually the highest here. And in the middle, since the velocity is not really changing, it's really low and actually drops to 0. Shear goes hand in hand with viscosity, because the higher the shear, the lower the viscosity of the blood. This is because shear helps to pull the elements in the blood apart, which decreases its viscosity. This means that the blood's less viscous at the vessel walls and more viscous at the middle of the vessel. Now let's say that all that blood's somehow moving at the same velocity. Well, in that case, if you plot it out, there's no change in velocity across the blood vessel. And that makes plotting shear pretty easy. Since there's no change in velocity, there's no shear. Alright, as a quick recap. The Reynolds number is written as RE equals density times diameter times velocity over viscosity, and is a way to predict when fluid's either going to be laminar or turbulent. In general, Reynolds numbers below 2000 will have laminar flow, and Reynolds numbers above 3000 will have turbulent flow. Furthermore, differences in velocity across a blood vessel causes shear. What's up guys, Tanner here. Thanks for watching that video on laminar and turbulent flow, which is very fluid dynamics-y, and hope you learned something because I really enjoyed making it. I really like physics and equations, and this sort of brings me back to my biomedical engineering days. So that was awesome. I hope you enjoyed it. And if you want to do like a deeper dive into this kind of topic, you should for sure head over to our platform, which is osmosis.org. We have a ton of flashcards, quiz questions, and just awesome tools to help you learn medicine. So if you're interested, definitely head over there to osmosis.org and make an account. Otherwise, you can always support us by subscribing to our channel and donating on Patreon. This particular video was written by Andrea and edited by Rishi. I did the animation and the voiceover, and Yifan did the editing. And that's all I got. All right, guys. See you later.